Just look outside your window. Go on. Chances are you can see them. Power lines. They crisscross the sky, and they're so common we barely even notice them anymore. But what you're really looking at is a story of some seriously clever engineering hiding right there in plain sight. I mean, think about it. These towers, these wires, they are the silent, hardworking backbone of our entire modern world. They're basically the arteries that deliver the energy powering everything from the phone in your hand to the lights of an entire city. So what does it actually take to get that power to you, safely, reliably, and without breaking the bank? What are the incredible engineering puzzles that have to be solved just to keep these lines standing? Well, that's what we're going to get into.
You see, the whole mechanical design of a power line, it's literally a high-wire act. It's this incredible balancing act between massive physical forces and, you guessed it, cold hard cash.
And it all comes down to this one core principle. Seriously, this one sentence right here, it guides almost every single decision an engineer makes. It's not about building for the absolute apocalypse. It's about building for the worst stuff that's actually likely to happen.
So what's the actual difference here? Worst probable? That's like designing for heavy ice buildup or the strongest winds you'd normally expect in that area. But worst possible, we're talking about a direct hit from a once-in-a-thousand-year superstorm. To build for that, your towers would have to be built like bunkers. And the cost? It would be so insane that your power bill would be too.
And that's the key takeaway, right? Engineers are in a constant state of trade-off. They're trying to build a grid that's tough enough to handle what nature will probably throw at it, but also in a way that keeps electricity affordable for all of us.
All right, so let's zoom in a bit. Let's talk about the heart of the power line itself, the conductor. That's just a fancy engineering term for the wire. And trust me, choosing the right one is where this whole balancing act gets really interesting.
Okay, so if you were an engineer building the perfect power line from scratch, this right here would be your dream wish list. You'd want it to be amazing at conducting electricity, obviously, but it also needs to be super strong, really light, dirt cheap, and it can't stretch or shrink too much when it gets hot or cold.
Yeah, that's a pretty tall order. Which brings us to the two main contenders for the job, good old copper and aluminum. And this image, it just perfectly shows their biggest difference. For the exact same electrical performance, aluminum is so much lighter than copper. And when you're talking about stringing wires for miles and miles, that is a huge, huge deal.
So when you lay it all out like this, the trade-offs become crystal clear. Aluminum, it's the undisputed champ when it comes to weight and cost. Big, big wins. But, and it's a big but, it's got a major weakness. It's not as strong as copper, and it expands more in the summer heat. And that can cause the lines to sag, sometimes dangerously close to the ground.
So there's the puzzle, right? How do you get all the benefits of aluminum, the low cost, the low weight, without its big downside, the lack of strength? How do you keep the wires from snapping under their own weight or when they're loaded with wind and ice?
Well, the answer, it turns out, isn't about choosing one or the other. Nope, it's about combining them in a really, really clever way.
Okay, so first thing you need to know is that power lines aren't just one big solid wire. They're what's called stranded. It just means they're made of a bunch of smaller wires all twisted together. Think about it like a rope. It's way more flexible and a lot stronger than one single thick thread would be. Same idea here.
And this is where the real genius kicks in. Engineers came up with something called ACSR. That stands for Aluminum Conductor Steel Reinforced. And this cross-section shows you exactly what's going on. You've got a core of super strong steel strands, and then it's wrapped in layers of aluminum strands.
It's just such an elegant solution, isn't it? The steel core has one job: provide the muscle, the strength to handle all that tension and weight. And the aluminum on the outside? It has one job too: conduct the electricity. So you get the strength of steel, but with the lightweight and low cost of aluminum. It really is the best of both worlds. Okay, so you've got these super clever conductors, but of course, they need something to hold them up in the air. So let's talk about the grid's backbone, the line supports, or, the towers and poles. And no surprise here, just like the wires themselves, the towers have their own pretty demanding wish list. They've got to be ridiculously strong to hold up the lines, plus any ice and wind. But you also want them to be as light as possible, cheap, last a long time, and, this one's important, be easy for line workers to climb and do maintenance on.
Now, the simplest and most common support you're going to see, especially in your neighborhood, is the classic wooden pole. Their biggest pro is simple: they are cheap. But the cons are pretty significant. They don't last forever.
maybe 20, 25 years before they need to be replaced. And they just don't have the raw strength you need for those massive high-voltage transmission lines that cross the country.
Right. For the really big jobs, the long-haul power transmission, you need the heavy hitter. You need the stronger alternative, the steel tower.
These steel towers are way, way stronger. That lets you have much longer distances between each tower. And they last for a really, really long time. So what's the trade-off? Well, they cost more to put up, and they need regular maintenance, like painting or galvanizing, to keep them from rusting.
So, we've talked about the wires and the towers. But believe it or not, that's still only scratching the surface. The complexity of this whole thing goes way deeper.
I mean, just think about it. Engineers have to map out the entire route, factoring in the terrain. They have to calculate the exact amount the wire will sag in the summer heat to make sure it never gets too close to the ground. They have to pick the perfect insulators, those glass or ceramic discs, to stop billions of volts from shorting out on the tower. They even have to decide on different grades of construction depending on if the line is crossing an empty field or a busy highway. It's just a massive, mind-bending puzzle with a ton of variables. So, the next time you're outside and you glance up at those familiar lines stretched across the sky, maybe you won't just see some poles and wires. Maybe, just maybe, you'll see this incredible, delicate balancing act. A quiet marvel of engineering that's working 24/7, all to keep our world switched on.